of mu also, or they are mixed together. Now let's consider this example, like again the uniform example. Here the range of x depends on parameter. Okay. Sorry. So find a sufficient statistic for theta. Okay. So let's use this Nameless factorization theorem. Okay, so our likelihood function is 1 over theta to the n. Okay, and we have xi less than or equal to theta case. Okay. Okay, so we don't have any statistic here, right? So we have only 1 over theta to the n, but no other statistics. So what we have to do here, focus on the range. One of the conditions that we are using in the Nameless factorization theorem is that the conditional range of xi given, so conditional range of xi given a sufficient statistic y is independent of theta. So here we have a range of xi depends on theta. So we have to think about if which statistic is given to me, which upper bound for xi is given to me as a statistic here. I don't need to know this theta. Okay, so we need to find an upper bound of xi, and one of the statistics should give us some boundary, upper boundary for all x values. Okay, so let's write this range in an ordered form again. Theta. So let me actually write one more thing. N minus 1, xn, and theta. Okay, so we have to think, we have to develop this kind of logic here. So here, this is the upper boundary, xn and theta. So these are the upper boundaries for theta. But if, so these are all ranges for x values. But if I know xn, if this value is given to us, if xn is given, so let's say we know the value of xn, let's say it's 5. Okay, so this means that all the values, all the x values, x1 to xn minus 1 should be between 0 and 5, right? So we don't need to know what is theta. So we have a narrower, we have more information actually. We have a narrower range for all xi values. Given, if xi is given, then we don't need to know theta. So we have a narrower range, right? Okay, so each value is here, 0 to xn, theta is somewhere here. So if I know this, so I know that all the other xi values lies in this range. Okay, so I don't condition range of xi with this knowledge does not depend on theta. Okay, so I know that this should be my sufficient statistic then. Okay, so this should be my sufficient statistic for theta. But I have to write my likelihood function as a multiplication of k1 and k2. Okay, so then I have to create it because I am using Nameless factorization theorem. And theorem says us that we have to write likelihood function as a multiplication of k1 function, which is a function of a statistic and unknown parameter, and multiplication of k2, which is a function of constant or other statistics. Okay, so I have to write my likelihood function in this form. Then I can apply Nameless factorization theorem. To be able to apply this theorem, I have to write my likelihood function in this way. Okay, so I know this part right now. 1 over theta to the n, 0, xi, and xn. Okay, so this part is okay. My conditional range of xi given xn not depend on theta. But I have to write my likelihood function right now as a multiplication of two functions. At this point, we are using indicator functions. Okay, so here we don't have proper k1 and k2 K2 functions. And to be able to apply the Nameless factorization theorem, we need to use the indicator functions. Actually, these are also known as dummy variables if we use them as a dummy variables. And by using that, basically, we will carry the information in the boundary inside the likelihood function. Okay, so what we will do actually, use this inside of the likelihood function by using the indicator functions. Okay, so how can we do that? So let's see what is an indicator function first. Let me give you the definition. Indicator function. Okay, so if, let's say, this A, capital A, is a set, okay, then the indicator function of this A is defined as indicator function I. Okay, I shows us an indicator function that's based on this set A. So it will take value 1 if our x is inside. So let me put x also here. Our x is in this set. Okay, 0 if it is not in this set. Okay, so like this case, so we have to create our likelihood indicator function as if our function is in this range or not, and put it an indicator function in the likelihood function. Okay, so let's try to do it for our case. So this is the definition of an indicator function. So for our example, let's create it. So we have 1 over theta to the n. Okay, so we have for each xi value, I from 1 to n, we have an indicator function, and each xi value is in this range. Okay, so if xi values are in this range, we will get 1. So our likelihood function will be just 1 over theta to the n. If xi is not in this range, 0 theta range, then likelihood function will be 0. Actually, we are not changing anything, just putting the range information into the likelihood function as this multiplication and using this indicator function. So it just takes value 1 or 0. If it is in this range, it will take value 1. If it is out of this range, it takes value 0. So let's try to write this function. So let's use order statistics here. Then if each xi value is between 0 and 1, so it will take value if and only if then the first order statistic is greater than 0 and the nth order statistic is less than theta. Okay, so if this is the case, it will take value 1, right? The minimum 1 should be positive, maximum 1 should be less than theta and also greater than 0. Okay, then let's write our likelihood function again. So using this information, okay, so we have a range that our xn function is between 0 and theta, okay, and we have an indicator function from 0 to infinity, this one here, x1. Okay, so basically we use this one as an indicator function here, we use this one as an indicator function here. So these are just 1s and 0s. Okay, so this is 1, this is n. Okay. So we created two functions. One here, which is a function of theta and a statistic, and theta and xn cannot be separated. So this is our k1 function. Y is nth order statistic and our unknown parameter. So this part does not depend on theta or the statistic xn. So this is our k2 function. Not depend on theta. So by the theorem, by the Nameless factorization theorem, y equals nth order statistic is a sufficient statistic for theta. Okay? Okay. So if you have more than one parameter, so we are using the similar thing actually. Okay, so let's say, or before the example, maybe I have to say this. If we have more than one unknown parameter, we will have more than one estimators. Then in this case, how we are finding the sufficient statistics, again, let's say we have just two unknown parameters, then we will have again k1 and k2 functions here. So we will have y1 and y2 to estimate unknown parameters θ1 and θ2, and we will have to have a function of θ1 and θ2 and these statistics. They should be in inseparable form. And again we have the k function, k2 function, which is just a function of xn or constants. So this part not depend on any theta, θ1, θ2, also in the conditional range. So this is important. Okay, so if this is the case, then y1 and y2 is jointly sufficient statistic. So I'm writing in vector form here. Okay, so they are jointly sufficient statistic for y1 and y2. So we cannot say that y1 is a sufficient statistic for θ1 and y2 is a sufficient statistic for θ2. These are jointly sufficient statistics for these two. Okay, so we cannot separate them for multi-parameter case. Okay, so we need to know both y1 and y2 to be able to estimate θ1 and also θ2. So let's consider this example. So let's say we have a uniform distributed random variables with on the range θ1 and θ2. So here are find a joint sufficient statistic for θ1, θ2. Okay, so let's write the likelihood function. So we have θ2 minus θ1 to the end. Again, we don't have any statistics, just a function of parameters here. But again, when we look at the range, range depends on parameters. So which two statistics are given to me, then the range of xi is free from θ1 and θ2. Again, we have to focus on the upper bound and lower bound for xi. Here, if we write our functions like that, order statistics, by using order statistics, if we write our whole range like that, each xi value should satisfy that. And here θ1 depends on x1 here, θ2 depends on x2, xn here. If x1 is given to me, then I don't need to know what is θ1. Or again, with the same logic, if xn is given to me, then I don't need to know what is θ2. So I will know that each xi value should be between this range if these are given to us. If x1 and xn are given to us. We do not need to know theta 1 and theta 2. Okay, so basically conditional range of xi given x1 and xn is free from theta 1 and theta 2. Okay, so we know that which statistics should be are sufficient statistics. Okay, so we have to put this information into the likelihood function using again indicator functions. So theta 1, theta 2, 1 over theta 2 minus theta 1 to the n. Again multiply each xi value, indicator function, each xi value should be between theta 1 and theta 2. Okay, I from 1 to n. So we can write this as a as actually this indicator function. Okay, as each xi value, or let me say x1 should be greater than theta 1 and xn should be greater than less than theta 2, and also other xi values should be between x1 and xn. Okay, so if we write our likelihood function this way, 1 over theta 2 minus theta 1 to the n, and put indicator function. So we have a range for x1 which is theta 1 to infinity. Okay, and we have an indicator function for xn. So we have to combine them, actually minus infinity to actually the lower bound should be theta 1 here, to actually I don't need to write this one, sorry. Okay, minus infinity to theta 2 xn, and we have an indicator function for each xi value, and they should be between x1 and xn. Okay, so we created our function. So these are all functions of theta 1, theta 2 and sufficient statistics. So all this part is our k1 function, where y1 is x1, y2 is xn, and we have two unknown parameters. So since we don't have k2, let's write it as 1 k2 function, vector of x values. So by Nameless factorization theorem, y1 x1 and y2 xn is a joint sufficient statistic for theta 1, theta 2. Okay, so here we don't say that x1 is for theta 1, xn is for theta 2. Actually, we will see that we will need both of them to be able to estimate theta 1 and theta 2 later. Okay. But we can say that if theta 1 is known, then the nth order statistic is a sufficient statistic for theta 2. And if theta 2 is known, x1 is a sufficient statistic for theta 1. But if both of them are unknown, these two are jointly sufficient statistic for theta 1 and theta 2. Okay. Let's give a break now and then we will continue.